AP Physics, Injuries in Automotive Accidents by Nick Pastore. Today I'm going to be talking about the different types of automotive collisions and the most common injuries that are a result of them. Then I'll be tying in Newton's 3 laws to explain the motion of the human body during car crashes. First, we're going to start off with head-on collision injuries, which include lacerations, burns, broken bones, traumatic brain injury, and organ injuries. Lacerations are caused from broken glass. Burns are caused from abrasions from the asphalt on the road if a driver is thrown out or if parts of the car catch on fire. Broken bones can range anywhere from a broken rib cage to broken arms to even breaking the spine. This happens when the driver comes into contact with a blunt object on the interior of the vehicle or is also launched out of the vehicle. Traumatic brain injury can occur when the force of the crash causes the brain to accelerate and recoil in the skull. Blunt trauma could also be a factor in traumatic brain injury when the head strikes something inside or outside of the car. Mild cases include concussions. However, severe cases include loss of brain function and possibly death. Organ injuries happen when the organs move around as a result of the crash and can be impaled or burst on the inside. Help may take too long to arrive for an organ injury, and this can have fatal repercussions. Next, rear-end collision injuries include a sprained wrist, stress fractures in the arm, joint damage, muscle bruising, and whiplash. A sprained wrist can happen if the hands are on the steering wheel, which bends back the tendons in the wrist severely, and the tendons can shift due to the acceleration alone. Stress fractures in the arm can happen when the hands fly out of control and slam parts of the car. Joint damage occurs from the acceleration alone, which can shift the joints around. Muscle bruising would happen with contact from a blunt force object. And whiplash is an injury which involves the muscles, discs, nerves, and tendons in the neck. The neck moves from rest to high speed due to the force of the crash, and since it moves quickly back and forth, this can potentially damage the muscles, tendons, and discs. Side impact collision injuries include whiplash, a fracture in the hand, a broken arm, ribcage damage, leg injuries, and spinal cord damage. Whiplash occurs in the same way as the rear end collision. A fracture in the hand happens when hands swing violently and hit something inside the car. A broken arm occurs in the same fashion, where the arms swing out of control and hit something in the car. Ribcage damage can occur if the car crushes the ribs, or if the airbag hits the ribs in a certain way, it could possibly break or bruise the ribs. Leg injuries happen if the car crumples and crushes the legs, and this honestly depends on how the car folds in on itself during the collision. Spinal cord damage could result in paralysis, and it's more likely to happen on the driver's side. The spine and back could get crushed by the car, and the driver could slam into a blunt object and sustain a spinal cord injury as well. Collisions and Newton's laws. The first law of motion states that an object will not change its motion unless acted upon by an unbalanced force. The takeaway from this is that the driver is more apt to change motion as a result of the crash rather than the car. The second law states that acceleration equals force by mass. The mass and acceleration share an inverse relationship. As mass increases, acceleration decreases. Drivers have a small mass compared to that of a car. Car crashes exert a lot of force. The driver's body, therefore, will accelerate at a large magnitude during the crash because of the relatively small mass. This means that the driver's body will be thrown at a velocity which has a magnitude depending on the acceleration size and how long the acceleration lasted. In big crashes, this means the body will be thrown at a high velocity, and this could lead to serious injuries. The third law states that for every action, there is an equal and simultaneous action in the opposite direction. This means the force exerted on the human by the car is equal to the force exerted on the car by the human in an accident. The driver's body will have to accelerate at a greater magnitude to match the force the car exerts on them. What is g-force? G-force is a unit of acceleration. 1 g-force is equal to 9.81 meters a second squared. This is relative to the acceleration Earth's gravity exerts. For example, 2 g's makes you feel twice your actual weight. This can be used to determine possible injuries of an accident. Now we're going to look at some real data of a crash test. As you can see, this is an acceleration versus time graph of different parts of the dummy when it went through the crash. The peaks mean that this is the maximum acceleration the dummy experienced. As you can see, the acceleration is expressed in G's and the time is expressed in milliseconds, meaning that the acceleration during the simulated crash occurred for a very short period. We can use this data to determine some possible injuries sustained by the dummy. Whiplash is a likely injury the dummy could have sustained during the simulated crash. This becomes a possibility when the head experiences at least 5 Gs of acceleration during a crash. As we can see, the head experiences around 33 Gs during the crash. Traumatic brain injury, on the other hand, is not likely. Using crash data from actual crashes, traumatic brain injury usually occurs when there's at least 50 Gs, and even so, there's only 16% of a chance for traumatic brain injury to occur during this type of accident. Crashes and collisions last for such a short period of time, there needs to be a lot of acceleration exerted for your body to get hurt. Internal organ damage is also not likely. Severe damage would require 65 to 75 Gs of acceleration to either the pelvic area or the chest. Shown by the data, the pelvis acceleration only reaches around 35 Gs, while the chest acceleration only reaches around 25 Gs. There might be some minor joint damage, but that would be all. No internal organ damage would be possible. Thank you guys for listening, and here's my bibliography.